is working on, excuse me, general aspects of fibrosis. And the main reason why we're doing this is to understand mechanisms of fibrosis and to develop targets, molecular targets, but also cellular targets that can be used for antifibrosis therapies. So this is a lab, I think it's already 2 years ago now, or let's say it was last year on Toronto Island. So one of the first physical meetings, which now obviously happen a bit more often, which is actually nice. Just as a reminder, I know this is about skin, but scarring that is very visible on skin, as you see down here in a scleroderma patient, or here in a hypertrophic scar after a burn incident, actually occurs in all organs. So I don't know of any exceptions, quite honestly. If you do, please let me know. So I'm not so bold when I say fibrosis occurs in all organs in our body. So that is just another way of saying scarring occurs in all organs of our body. And this talk is going to focus on implant fibrosis, and it has a relation to skin because the cells which react to implants, in our particular case, are skin cells or fascia cells. From the mouse, though. In all those conditions here, the one culprit which is common to those fibrotic situations is the myofibroblast. By the way, I don't know if you hear that, but timing is just perfect. Outside, they start now heavy construction. So if you're not disturbed by it, forgive me if every now and then I might be because of the noise that is here. So the myofibroblasts are common to all those fibrotic conditions because that's the cell which produces the scar tissue by making collagen and by organizing collagen into scar tissue. And that's a good thing because whenever an injury happens in our body, that injury needs to be repaired. And that repaired, unfortunately, is not equivalent to regeneration. That repair is more of a quick fix to prevent that we fall apart. And it's a very needed action. But if that action becomes excessive, we end up with hypertrophic scarring in skin or fibrosis in other organs. There's always, I mean, since its discovery 50 years ago, there's always a debate what myofibroblasts actually are and what cells you should call a myofibroblast. So most often, you would call a myofibroblast a mesenchymal cell that is activated in a tissue repair or fibrotic situation, which expresses smooth muscle actin, which is a specific actin isoform of smooth muscle cells in stress fibers or actin-myosin bundle. And that's where the name came from. The actin-myosin bundles actually promote contractile activity, and that's the myo part of the myofibroblast. Smooth muscle actin expression is very convenient as a diagnostic, but as the name may suggest, it's not specific to myofibroblast, and it's also not needed for the basic definition of the myofibroblast. So the most basic definition of a myofibroblast would be a contractile mesenchymal cell, which produces collagen or has produced collagen at some point along its way to becoming a myofibroblast. So don't be fooled. Smooth muscle actin is a great marker, and you're going to see it in some of my slides, but it's not a unique feature, and it's not a necessity for myofibroblasts to be called that way. Obviously, there are other states of activation that fibroblastic cells can attain. So in the skin, we often think of a fibroblast in a normal skin, that is, of a quiescent cell, which provides homeostasis of collagen by every now and then producing a bit of collagen and regulating its very niche environment. And those cells are then activated in an injury situation to proliferate, to migrate from a normal tissue site into a wound site. And while they migrate, they already develop some kind of contractile features or stress features. And then on site, they would start producing collagen to replace fibrin, typically, which is laid down initially during wound healing by collagen. So all these states, I'm not going to argue about that. They're activation states which happen during wound healing, which also exist in fibrosis, but they're not qualifying these cells to be myofibroblasts because they're missing one important feature, which is the contraction. So it's just no way a cell that does not contract would be a myofibroblast, just by the simple definition of the word. And there are other activation states that I'm not going to go into, which are secretory fibroblastic cells. And you'll see some of them on the right side in a second. So that's one part of the debate. The other part of the debate is, where do these myofibroblasts come from? And I'm not going to go into any detail, just to suffice to say that many different precursor cells can attain a phenotype that we would call a myofibroblast, and which have the role to repair tissue initially. That I think, this is a bit of speculation on my side or interpretation on my side, is wanted, because when an injury occurs in your body, it's never known, or the organism cannot know where the injury happens. So either you have specialized cells on site in every site of our body, which would be activated upon injury, or you give many different cells the option to become activated after an injury, which I think is evolutionary a much more likely situation. And the science tells us that that's actually the case. So you pick your favorite cell on the left side of this slide, and those would be all potential myofibroblasts. And then it comes down to debates which is the most important precursor of myofibroblasts. And I think that depends very much on the organ you're looking at, on the type of injury, on the severity of the injury, and the timing of the whole process. So that's like 10 years ago, I was at a conference when this precursor idea was starting, and every speaker gave actually a percentage of what they think their particular cells contributed. So fibrocytes, mesenchymal stem cells, parasites. And at the end, the chair of the session said, guys, I calculated all the percentages that you gave me, and I came to 340% of contribution if I sum it all up. So obviously there's a bit of a disconnect here. We'll know more with single cell RNA sequencing, and I'm not going to show you any t-SNE plots, promise, or UMAPs. And then the last part on this slide I just want to briefly comment on is the question, where do these cells go? How do they disappear, or why do they not disappear in fibrosis, whereas we don't see them anymore after a wound resolves? And there are different states which are apoptotic, senescent, or senescent secretory, which these myofibroblasts can attain. And whether or not they become apoptotic or senescent pretty much determines whether a wound resolves or not. There's much more to be learned about myofibroblasts, which I'm not going to tell you about. I'll invite you to look into this Journal of Cell Science poster paper that we wrote some while ago with the lab. There's one panel I want to focus now, which is mechanisms of how myofibroblasts are activated. They're, I say obvious, might not be obvious, but they're inflammatory factors, TGF-beta, most prominently, as you will see later, which activate precursor cells into myofibroblasts. But there are also other factors, most notably mechanical factors, which promote activation. So because it's not a coincidence that these contractile bundles we see in the cells are called stress fibers, because they are formed by these cells in response to mechanical stress. What you see here in the middle panel now are myofibroblasts. I believe these were from lung, mouse tissue or rat lung tissue, directly plated onto soft, medium, or stiff silicone elastomers. To give you an idea, 2 kilopascal elastic modulus. Soft is a bit softer than a gummy bear. Medium is a gummy bear stiffness, and 65 is the stiffness that these cells would see in a scar tissue, so rather stiff. Just to let you know that 65 kilopascal or scar stiffness is still 1,000,000 times softer than plastic dishes that we usually offer these cells to grow on in a culture environment. But I'm not going to comment on that very much longer. So because I always forget to thank people, these are the people that contributed to the project that I'm going to talk about, and how we think we can use this fact that myofibroblasts react to different stiff or different elastic environments by being activated or not in the context of implant fibrosis. So Nina is the first author of the paper I'm going to show, which was, she was helped very much by Ronan. Sander pretty much started the whole idea, and then Maya, Anne, and Stellar, which are all not in my lab anymore, except Maya, they helped along the way. So here's the clinical problem, as some of you may know. All implants that you put in the body create some kind of a reaction. And depending on the severity of the reaction, this so-called foreign body reaction, you get rejection of the implant or encapsulation. In the case of silicone implants for reconstructive surgery or aesthetic surgery, 30% of all implants, silicone implants, will be encapsulated by fibrotic tissue. And those 30% need to be reoperated after a certain while because the implant is deformed by the fibrotic contractile capsule, creating pain, discomfort, and obviously destroying all the aesthetic aspects that they might have been used for. And the industry spends billions of dollars, or it's actually not the industry, it's the patient spending billions of dollars to find ways of circumventing that fibrotic reaction. So there are several ways of how the surface of these implants can be modified with the idea that implant reaction fibrosis would not happen. And I just told you that the fibrotic cells are myofibroblasts, and part of their activation is mechanical nature. So Nina and Ronan asked the question, what happens if you provide silicone implants with a soft surface? Would that be sufficient to suppress fibrosis formation? It might be counterintuitive to think that an implant or a silicone implant, breast implant, is stiff, but it is. So the outer shell of these implants is a very robust polymer, silicone again, whereas the inside, and this is one where there's a breach or is a defect, the inside is usually filled with gooey material, less polymerized silicones, or even saline solution. But again, the outside of the implants is stiff at the cell perception level. If you measure it, it's around 2,000, 3,000 kilopascal, which again, you related back to the 2 kilopascal of the soft material, which suppresses the myofibroblasts, is 1,000 times stiffer already. So what we did in this study is obviously didn't use humans for those studies, but mice. We created mini implants which had a stiff interior core, the same stiffness that a human implant would have, and then coated these discs with either a soft layer, which is 2 kilopascal here in red on the right side, or a stiff layer, which is green, which corresponds to the stiffness of human memory implants. And those implants were then placed subcutaneously under the panicus canosum of mice in a kind of a crossover scheme here with stiff and soft implants. They were excised after different times after implantation and analyzed at first by histology. So this is a cross section now through a stiff implant after 7 days, stained for mesentrichrome. So what you see, everything which is blue is collagen or extracellular matrix. And for the purpose of this talk, I'm just going to talk about the dorsal side. I always mix it up. The ventral side of those implants, meaning which is away from the skin. We analyzed like the implants all around, but the results are pretty much the same, either dorsal or ventral. And the analysis is pretty clear. So over time, which is from left to right, if you analyze collagen layer formation on stiff implants, again with a stiffness corresponding to what humans would see, you get a robust formation of very thick collagen-rich layers from this mesentrichrome staining. Whereas if you provide the implants with a soft surface, which suppresses myofibrous differentiation, in culture at least, there's much less collagen accumulating. And this is the quantification on the right side, whereas 20 is about the baseline that you have in a normal skin as a collagen staining, and you see the nice difference in collagen accumulation over time. The same is true for myofibroblast accumulation that we stain here for smooth muscle actin. And again, on the stiff implants, we get dramatic increases of myofibroblasts up to day 28. And then same thing happens as with a skin scar. The scar is thinning and the myofibroblasts just accumulate in a very dense region where this whole process is pretty much suppressed by just putting a soft layer onto those stiffer cores of the silicone. I told you like briefly that TGF-beta is one pro-fibrotic factor or one pro-scarring factor, which dramatically increases myofibrous activation. And you can see here, if you stain for TGF-beta, in the region where the myofibroblasts are activated, there is no difference in total TGF-beta in myofibroblast or in the region where the myofibroblasts are sitting between stiff and soft implants. There's a bit of an increase over time, but there's no difference between the two stiffness conditions of the implants. However, if you look at signaling of TGF-beta, you get higher amounts of active TGF-beta signaling, which is indicated here by phospho-SMAD staining on the stiff implant surface. Again, this is like right at the surface where the myofibroblasts sit, where in contrast on the soft implant site, you do not have activation of TGF-beta or lower levels of activation of TGF-beta. So now what follows now is the most complicated slide I have for this talk. So TGF-beta is a kind of a weird growth factor. It's not secreted or ever secreted in its active form. It's always secreted in a latent preform. So you can think of TGF-beta being a candy, which always comes with the wrapper, and in order to be consumed, must be released from that wrapper. And Dean Shepard's group has shown, like in the late 90s, beginning 2000s, that integrins, cell matrix adhesion receptors, bind to the latent proform of TGF-beta and activate TGF-beta, although at the time it was not known how the activation is happening. And then the group of Dan Rifkin has shown that on the other side of the latent TGF-beta complex, TGF-beta can bind to extracellular matrix protein, in this case, one which is called LTP1, which provides mechanical resistance, and that resistance is needed for integrins to activate TGF-beta. Again, the process was not known how that works. And that's where my lab came in. That was in the, 2007 exactly, where we postulated that if fibroblastic cells can bind to latent TGF-beta and pull by contracting, that would be enough to release TGF-beta by a conformational change. And Pierre-Jean did a number of very nice cell culture experiments. Lara did single molecule atomic force microscopy, both showing that that's happening here. And I'll skip over those because they're not so important and because I'm running out of time. Now, are the integrins, which we know are expressed on fibroblastic cells to activate TGF-beta, expressed at the implant surface is the question here. And all integrins or all TGF-beta activation integrins are alpha V integrins. As you may know, that integrins always come with an alpha and a beta subunit. And the most prominent myofibroblastic or mesenchymal integrin activating TGF-beta is alpha V beta 1. There's no antibody against that particular alpha V beta 1 heterodimer, but there are antibodies against alpha V and beta 1, and both are upregulated on the stiff implant surface compared to the soft implant surface, if you just look for the amount of brown staining here. And you can also digest the fibroblasts out using a collagen reporter mouse and quantify the amounts of alpha V and beta 1 by flow cytometry, which pretty much shows exactly the same that you see here in the histology staining. So I'm not going to go into that much more. And this is, if I remember correctly, this is the last data slide. So the idea so far is that at the stiff implant surface, there is mechanical resistance or mechanically stiff material that directly activates myofibroblasts, but it also would contribute to the activation of TGF-beta because it provides more resistance to this pulling mechanism that I've just shown you. So if that is indeed true, if we would block the integrins that activate TGF-beta, we should be able to reduce implant fibrosis even on stiff implant. And that's exactly what we do here. So we implant stiff implants on one side of the mouse and an osmotic pump on the other side of the mouse, which releases a compound that inhibits alpha V integrins called CWHM12. Never mind. And as you can see already in the overview here, there's a nice reduction of the collagen-rich layer in the condition where that compound has been released. In a nutshell, the capsule thickness measured by collagen is basically completely suppressed by this integrin inhibitor, as is collagen density and alpha-synuclein expression density at the surface of these implants. So all of those fibrotic markers are downregulated when you block the integrins that activate TGF-beta. Those integrins, by the way, are in this particular context, not important for cell adhesion or cell migration. So we have no problems of myofibroblasts arriving at the site here. In the interest of time, I think that's a short talk, so I don't have to go into the details of the summary here. Just one side note that I didn't talk about in this particular paper, we also showed that the integrins themselves are obviously known to be mechanically regulated and mechanically activated, and that activation of the alpha V integrins or alpha V beta 1 integrin is also influenced by the stiffness of the surface. So everything pretty much is geared towards activation of those cells. And if you either block the integrins or you provide a soft layer on the surface, you pretty much suppress the whole fibrotic reaction. Thank you very much.